Today we have our last day of talking conceptually about the derivative before we get into the nitty-gritty of how to calculate the derivative efficiently. So by the end of today, I want to review a concept from pre-calculus about a function being increasing or decreasing. And then I want to introduce this idea of the derivative not just as a number, but the derivative as a function. We're going to relate the sign of the derivative as a function back to the original function and whether the original function was increasing or decreasing. We can do this from formulas, graphs, or tables. And then we're going to practice relating the graph of the function f of x to the graph of its derivative f prime. So recall from pre-calculus that a function was decreasing if the outputs go down, hence decreasing, when the inputs go up. So a decreasing function, graphically speaking, has the appearance of pointing to the bottom right. As your inputs go up and you move to the right, the y values on the graph go downward. Contrast that with an increasing function. A function is increasing if the outputs go up when the inputs go up. So graphically, an increasing function seems to be pointing toward the top right, because as you move to the right and the inputs increase, then the graph rises and the outputs also increase. For example, let's suppose that we returned to this function that we looked at briefly yesterday, and let's analyze this function using this language. Someone says, on what intervals is this function increasing? Now, yesterday when we analyzed this graph, we saw that the function was increasing and was slanted upward between t equals 0.7 and t equals 2. So that would represent one time interval where this function is increasing. And since it said interval, I'm going to write this in interval notation between 0.7 and 2. We also see that this graph is slanted upward at every point from 3.5 to the final time at t equals 4. So the graph is also pointed upward. The function is also increasing from 3.5 to 4. At which points on which intervals is the function decreasing? In this case, we're looking for areas where the function's graph is pointing to the bottom right, is tilted downward. And so this occurs basically in the other locations on this graph, from the initial time at time t equals 0 down to the time 0.7. And where else do we see this graph decreasing? We see the graph going downward from t equals 2 down to this bottom point at 3.5. Now those of you who remember yesterday's work may notice that these intervals overlap incredibly with the regions where the derivative was positive and the regions where the derivative was negative. And that's definitely no accident. The function is increasing if it's pointed upward, and whenever the function is pointed upward, the slope of the tangent line is a positive number, and therefore the derivative is a positive number. Having concluded the review, I want to begin to discuss this idea of the derivative not just as a singular number, but as a function. A function is just a mathematical object where you can plug a number into the function and get a number out. So what would be the input of the derivative f prime the input of the derivative would be an x value. We're going to feed an x value. We're going to feed a location into the function, which is called f prime. What is going to come out of f prime? The derivative function is going to tell me the slope of the tangent line at that x value. Or, put another way, it will output the instantaneous rate of change of the function at that x value. Now, when we wanted to find the derivative of a function at a specific location, we had this formula, the limit as h approaches 0, f of a plus h minus f of a divided by h. That gave us the derivative at a specific x value, the specific x value x equals a. And what I want to do is I want to remove that specificity and change this formula so that it applies not just to one specific value of a, but to any x value you might be interested in. So instead of having a specific number a, I'm going to remove a and just put the variable x in its position. If you want a function into which you can plug an x value and get out the slope of the tangent line at that x value, then all you have to do is use this formula, the limit as h approaches 0 of f of x plus h minus f of x all over h. And let's notice that the derivative function, the function who takes an x value and produces the slope of the tangent line, the notation for the derivative function is f with this apostrophe parenthesis x. We read this out loud as f prime of x. Another way to represent this quantity, which is slightly less common, is by df dx. So let's go ahead and practice calculating the derivative function. Not the derivative at a specific x value, but a function that could be used to find the derivative at any x value. We have f of x equals x squared, and we want a formula for the derivative function f prime at x. So what I'm going to do is I'm going to take the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now the process is very similar to all the other difference quotient calculations that we have done up to this point. It can just be slightly more challenging sometimes because now we have two variables in this calculation. We have h, but we also have x floating around. But I'm going to start this process in exactly the same way. I'm going to try and figure out what is f of x plus h and what is f of x. I'm going to try then to replace those quantities in this formula so I can simplify. Now f of x is given to me as x squared, and f of x plus h must therefore be x plus h squared, because f is the function that squares things. If I simplify that, I'll get x squared plus 2x times h plus h squared. Now let's take that data and let's put that back into the difference quotient formula. So f of x plus h we now know is x squared plus 2xh plus xh squared. Take away x squared. Now just like when we did this calculation with numbers instead of x's, we can take the x squared minus x squared and those will cancel out. That leaves us with the limit as h approaches 0 of 2 times x times h plus h squared over h. And just like we did in the previous calculations where instead of x we had a number, we can factor h out of the numerator. Just like before, we can cancel those h's. And just like before, now we have a fully simplified function. So instead of letting h approach 0, we can plug 0 in for h in this formula. So what have we concluded? We have concluded that if you want a formula that will tell you the derivative of the function at any given point, all you have to do is take that x value and plug it into the formula 2 times x. So for example, the derivative at x equals 1, if you wanted to find the derivative of x equals 1, you no longer have to go through this difference quotient process. You've done it once and for all. If you want the derivative of the function at x equals 1, you can now plug in 1 to this formula. So the derivative of this function at x equals 1, the slope of the tangent line would be 2 units. Once again, now that we have this formula, we could very quickly find the derivative's value at any other x. For example, there's nothing stopping you from finding the derivative at minus 1. Now that you've found a general formula for the derivative at minus 1 can be obtained just by plugging minus 1 into your formula. Result minus 2. So, in summary, when would you use this formula here? You use this formula when you want to calculate a single difference quotient once and for all, and then you can use the result of that difference quotient to determine the derivative of a function at any x value you want. Now, because f prime of x is also a function, f prime of x also has a graph. Every function has a graph, and so does, in this case, f prime of x. So I wonder if there is any relationship between the graph of the original function f of x and the graph of the derivative function f prime of x. Let's check it out with this function that we worked with in the previous example. Our original function was f of x equals x squared, and our derivative function was f of x equals 2x. Here I am on Desmos. I've graphed the original function f, that's x squared here in blue, and then I've graphed the derivative function, which we found was equal to 2x. So let's see if we notice any relationship between the graph of x squared and the graph of the derivative 2x. Now notice that x squared is increasing everywhere to the right of 0. Everywhere to the right of 0, x squared is tilted upward. As a result of that, the slope of the tangent line on the right side of the graph will always be a positive number. So, the derivative will always be a positive number on the right side of the y-axis. That is reflected by the fact that 2x is going to be a positive number and has a positive output everywhere to the right side of the y-axis. Likewise, x squared is decreasing everywhere to the left of the y-axis. On the left side, x squared points downward, and the slope of the tangent line is a negative number. So the derivative is a negative number, and that's reflected by the fact that the derivative function is located in the negative zone, here where the y values are negative numbers. Notice that at x equals 0 exactly, the function x squared is perfectly flat. That's where the vertex of the parabola is located, and the tangent line would be horizontal at this position. Since the tangent line would be horizontal, the derivative would be 0. And that's reflected by the fact that 2x outputs a 0 value at that position. So to summarize some of the observations that we made, one observation is that when f of x is increasing and tilted upward, f prime of x was positive. The y values on the graph were positive. The graph was above the x-axis. When we looked at the left side of the parabola, and the original function was decreasing, in all of those positions, the derivative was negative. And graphically, that means that the derivative is going to be below the x-axis. And in situations where f of x was flat, the derivative's value was 0. And at such a point, the graph crossed the x-axis. Those observations were true for the case of f of x equals x squared, but in general, those same facts are true for any function f of x. If you have any function f of x, and you're representing the derivative function by f prime of x, the following three facts are true. If the original function is increasing, the derivative is positive. So I'll represent that by greater than 0. If the original function is decreasing and tilted down, then the derivative, the slope of the tangent line, is negative. And if the original function is flat, f prime is going to be equal to 0 exactly. So using these principles, you can actually get a pretty good understanding of the graph of the derivative function f prime, even without necessarily being able to calculate the formula for f prime. In the case, for example, here of f of x equals sine x, you're going to have a really hard time calculating f prime without using a bunch of somewhat obscure trig identities. So let's see if we can get a sketch of the graph of f prime for the function sine of x without having to use the difference quotient formula. So I'm going to use the principles that we outlined on the previous couple of pages to help me to make this sketch. And generally speaking, the easiest thing to start with is these locations where the graph of the original function is flat. The original function f of x equals sine of x is flat at pi over 2 minus pi over 2, 3 pi over 2 minus 3 pi over 2, and so on, off to infinity. Now everywhere the original function is flat, the derivative is 0. So I'm going to mark these locations where the original function is flat, and they're going to translate to locations where the derivative function has a y value of 0. They're going to translate to locations where the derivative function crosses the x-axis. So all these green points marked below are points which are on the graph of f prime. The next thing that I'm going to note is that every location where the original function is increasing, the derivative function is positive at such locations. So here, dead center, the original function is increasing, it's tilted upward. Over here, between 3 pi over 2 and 5 pi over 2, same thing. The original function is pointed upward. Over here to the far left, the original function points upward. Now at all three of those locations, the derivative function is positive. So at all three of these locations, the derivative function is going to live above the x-axis. So I'm going to try and connect these green dots in such a way that the graph is above the x-axis. And there's not really many ways to do that, so I'm just going to connect the dot, go from the dot up, and then back down to the dot. Same thing between these two. I have to connect these dots, but I have to be above the x-axis, so I'll go up for a while and then I'm forced to come back down. I need the graph to connect these two dots, but I need to be above the x-axis, so I'm going to come up for a while and then come back down. Okay, now let's look at a few of these other locations. For example, between negative 3 pi over 2 and negative pi over 2, the original function is slanted downward. Same thing is true between positive pi over 2 and positive 3 pi over 2. And if the original function is slanted downward, that forces the derivative to be negative. So where will I graph the derivative in that case? The graph of the derivative is going to have to be below the x-axis. So I need to connect these green dots, but I need to connect them with a graph that is negative, that is below the x-axis. So I'll go down for a while, but eventually I'm forced to come back up. I'll go down for a while, but eventually I'm forced to come back up, and so on. Now, does this graph, this rough sketch of f prime of x, kind of look familiar? Have you seen this graph before? This is looking an awful lot like the graph of cosine. It turns out to be not a coincidence. It turns out that if you take the derivative of sine, using the difference quotient formula, using the trig identities and all of that, it turns out that f prime actually is equal to cosine. But that's a conclusion that you can reasonably make just looking at the graph of sine x and sketching a graph of f prime. That concludes today's material. We reviewed the concept of what it means for a function to be increasing versus a function being decreasing. After we reviewed that, we introduced the idea of the derivative as a function. The function's input was a horizontal position, was an x value, and the derivative's output was the slope of a tangent line to the original function at that point. We then gave the difference quotient formula for the derivative function. And we practiced using that formula in the case of x squared. Then we thought about the graph of the derivative function, and we looked at the relationship between the graph of the original function, f of x, and the graph of the derivative function, f prime of x.